think it is fine. Yes, a very good morning to all of you. Am I visible and audible to everyone over here? Yes? Yeah, thank you, Gayatri. Yes, a very good morning to all of you, and I hope all of you are doing well. Thank you all for your lovely wishes. Thank you. And I hope all of you are doing well, right? And how did you write your test, by the way? Was it good? It was fine. Okay. How much we are trying to able to score in chemistry as far as chemistry is going on? Okay, Ashfa, good. 670 is good. Okay, fine. That's good number. Try to achieve like more than 150, that will be like much more justified, because anyhow chemistry is a very good scoring subject. It will enhance your marks. Okay. Acha, in the last class, I think I have finished off with the ionization energy application, if I'm not wrong. We have finished that, right? Okay. So today we are going to start off with the next property, which is electron affinity, okay, or else the electron gain enthalpy. So let us start this session, okay. So we are going to start off with electron gain enthalpy, which I'll be denoting it as delta HEG, or sometimes, in many books you might even find like this, delta EGH. Anything is fine. H is anyhow, it is the symbol for enthalpy over there, right? Or else we'll be talking about electron affinity, right? And here, in short, we are going to write down it as electron affinity as this, okay, EA. Now, what does it basically tells you? What exactly is electron gain enthalpy? Now, let us try to break this word, okay. When I say enthalpy is basically energy changes which is associated with any process. That's what is enthalpy. Now, in the process which we are talking about, what is the thing which is going on? It's basically electron gain. That means some species is there, or that is a neutral atom which is trying to accept electron, right? So we have broken down the entire term into parts to understand this, so that it becomes more easier, right? So enthalpy is energy change associated with any process. Electron gain, which particular process I am referring to? I am referring to basically electron gain here, okay. So now what we do is basically, if at all I take a neutral isolated gaseous atom, and when it accepts an electron, definitely what will happen? It will get converted into X minus. Then whatever are the energy changes associated, whether it is like endothermic or exothermic, whatever are the energy changes, that is referring to the electron gain enthalpy. Okay. So I'm writing here delta HEG negative, which is general case. Okay, generally. Okay, it will be exothermic. It could be positive also, but I'm saying that it is only for few elements, only for few, right? But in general it is negative. Okay, so what I'm going to write down, negative means the energy will be released. So I'm going to write down, when I'm writing down the definition of electron gain enthalpy, which says when an electron is added into an isolated neutral gaseous atom, so that anion can be formed, and the energy changes associated with the process is known as electron gain enthalpy, right? I'm just writing it like that. Okay, so that's what is electron gain enthalpy. Make sure that all of you are writing this, and then we are going to proceed further. And again, mind well, I didn't explain anything about the electron affinity at present. I just spoke about electron gain enthalpy. Okay. And once you are done writing, just raise, like, you can just do thumbs up so that I can understand that. Okay. Now here I am writing, suppose there are like two elements, two isolated gaseous atom which I am talking about, right? One is suppose X gas plus electron, it's becoming X minus in the gaseous form, and let us say delta HEG is minus 10 kilocalorie per mole. I'm just writing down the, I'm not writing down the unit, but definitely somewhere either in electron volt or kilocalorie per mole. Then I'm having Y, isolated Y gaseous atom, and I'm saying Y minus gaseous one, and I'm having electron gain enthalpy, suppose here as minus 40, right? Now here I'm asking you in the form of a question only, right? Let us say this is electron volt only you think of, okay? So what I'm saying here is, which element has, first one, higher electron gain enthalpy, and which has higher negative electron gain enthalpy, right? So the answer according to you might be, majority of you might say it is minus 10, which I'm able to see, right? But the thing is, when I'm asking about electron gain enthalpy, here you just have to see in which particular atom is able to accept the electron and it is able to release more amount of energy, right? So you just have to look by the magnitude here for electron gain enthalpy if I ask you. So higher electron gain enthalpy, my answer would be here, it will be the Y, and which has negative electron gain enthalpy, it is again Y, because we always compare the negative electron gain enthalpy only, right? So that's the reason I'm saying which is higher negative, whatever the term they are using, they are ultimately asking you which one is having higher electron gain enthalpy only. Getting it? So there should not be any confusion here. Because we generally do not compare for the elements which have got positive electron gain enthalpy. Positive electron gain enthalpy tells you that that particular element, it doesn't want to accept electron. You are giving energy to it so that it accepts the electron, right? So which is endothermic process. I hope this is clear to you. Okay. So make sure you are writing this quickly. Okay. Now let us come down to electron affinity definition, right? So what I'm going to write down, the energy released when an isolated gaseous atom accepts an electron, right? That's what is electron affinity, right? Now the thing is, if at all I write something like this, X gas plus electron, it's forming X minus, and let us say I'm saying that delta HEG is negative here. That means when this neutral gaseous atom accepts electron, it liberates energy, right? Now what I will be saying here is electron affinity is positive, right? Now let me give you one more example. If I say I'm having Z gas plus electron, it's forming Z minus in the gaseous form. Here I'm saying the electron gain enthalpy is positive, but the electron affinity is going to be negative, right? So one thing which you are able to see from the data, whatever is the sign of electron gain enthalpy, the reverse sign is of electron affinity. That means I'll be able to write down this as electron gain enthalpy, or else the electron affinity is minus of that. Okay, so electron affinity is minus of electron gain enthalpy. That's what I'm going to write down. Now the thing is, you try to understand one thing. If any element, okay, it is happily accepting that electron. Here when I talk about affinity word means liking towards that electron. Okay, liking. Affinity in general means liking. So when I say electron affinity, it is basically liking towards that incoming electron. That means it wants to accept that electron, right? So if it wants to, if a particular element wants to accept the electron happily, I say that it has got positive electron affinity because it wants to, it has the liking. And what about this? When it happily accepts it, then basically it is becoming like it will be releasing energy. Okay. Now, listen for the another instance. Okay. Now, in this case, what I said that the electron gain enthalpy is positive. That means you have to supply energy. That means you are forcibly giving this element that particular electron. It doesn't want to accept. That means, suppose if at all I talk about neon is there, nitrogen is there, right? Beryllium is there. They all are having some or the other stable configuration, either half-filled subshell or else fully filled shell or subshell, right? So there, nobody wants to disturb their stability. So basically, they don't want to accept the electron, right? So they don't have liking towards the incoming electron. So I say that their electron affinity is negative. So when I talk about these two terms, electron affinity is telling you the liking towards that incoming electron. Electron gain enthalpy, whatever are the energy changes. If any element happily accepting the electron, definitely it is going to release energy. Getting it? Hopefully it is understood. Please write this down. So we always define electron affinity as the amount of energy released. Okay. Write this down, then we'll proceed further. Yes, hopefully people have written it. Now, if at all, let us now move on for next one. Second electron gain enthalpy. Enthalpy is always positive, right? Is always positive. That means suppose if I write something like a note here. So I am saying that suppose I am having X gas plus electron and it is becoming X minus in the gaseous form, and let us say this is electron gain enthalpy 1, it is negative, right? Then second electron gain enthalpy I am talking about, that what is going to happen, X minus 2, you are having delta Eg2, I am saying it is going to be positive always. This is the case always, right? Why it is always? Because the thing is, here earlier you were adding the electron into a neutral gaseous atom. Now what you are having is already anionic species is there, right? So when you try to add one more electron, there will be like more force of repulsion here, which will be existing, right? So because of that, this process, like if you still want to give that electron to that particular anion, you have to give sufficient energy to overcome the interelectronic repulsions there, right? So that is the reason we say that the second electron gain enthalpy for any element is going to be positive, right? Getting it? So you may feel like you are having suppose O to O minus. This is a very common question. O plus electron, it will be like O minus. And then O minus plus electron, you are getting O minus 2. You might feel, ma'am, O minus 2 is again having stable configuration, then still, how come? It is having basically the positive electron gain enthalpy. You will see that here it is delta Eg1 is negative and delta Eg2 is positive. So I'm saying that irrespective of whether you are getting a stable electronic configuration or not, it doesn't matter. Ultimately what it is second electron gain enthalpy and it has to be endothermic, right? So you need not get confused here, okay? And this is important. Please write this down, then we'll proceed further. Have you written this down? Okay, good. Now let us go for seeing the factors affecting electron affinity. Now see here we are just going to see what are those factors which are going to affect electron affinity, and now I'm not going to say about electron gain enthalpy because you understood, right? Because it becomes very easier to understand any factor in terms of whether it will help in gaining that electron or not, right? So that's the reason we are going to focus on factors affecting the electron affinity. Now first one is, if I talk about Z effective, right? This Z effective represents what? The nuclear force of attraction, right? So now if at all I say that Z effective increases, then what is happening? Attraction is increasing, and if attraction increases, size of that atom is going to decrease and hence electron affinity increases, right? Because the thing is, electron also wants to come to that particular atom where it is where it is feeling that attention, right? Suppose if you want to visit to any of your friend's house or else relatives house, and you go there and nobody is paying attention to you, as if like they are not at all bothered that you have even visited at their place, would you feel like to go there? You don't feel like, right? So you always want some kind of importance when you have visited someone's home, right? Similarly here also, if the electron is there, electron is trying to come inside the atom, right? So it wants that attention from the nucleus. So if at all it is not getting that attention, it doesn't want to come. That means what is that kind of attention which I am talking about? From the nucleus, it is basically the nuclear force of attraction which I am talking about. Okay, now let us go for the number of shell. Now for number of shell, if that increases, what happens? Size will increase. Size means definitely now you are trying to add the electron into a shell which is very, very already far away from the nucleus, right? So it becomes like the nuclear force of attraction decreases a lot there. So what we are going to say, that electron affinity is going to decrease. Okay. Then next is, suppose, stable electronic configuration. Stable electronic configuration. Now when we talk about stable electronic configuration, it is seen that those species which are having half filled or else fully filled subshell configuration, they do not show any electron affinity. That means if for rest of the elements, if the electron affinity is positive, for them it will be negative, right? That's coming absolutely from the value. Okay, so we can write down elements having half filled or fully filled subshell configuration elements having this half filled or fully filled subshell configuration do not show or do not show any electron affinity. You know? That means here you can just write down one note that in case of you're having beryllium, magnesium, nitrogen and all inert gases, right? For this, for beryllium, you are having magnesium, nitrogen and all inert gases. electron affinity is negative, right? For rest of the elements, electron affinity is basically positive. That means if at all I'm saying the electron affinity is negative, that means they don't want to accept the electron. That means what is their delta HEG is going to be? That is going to be positive. And here it is going to be negative. Getting it? Because they don't want to accept the electron, they don't want to lose their stability. Okay? That is basically your stable electronic configuration. Hopefully you understood. Then penetration effect, right? So when we talk about penetration effect here, so basically if at all I talk about lithium and suppose I'm talking about boron, it is 1s2 2s1, here it is 1s2 2s2 2p1, right? Now which one is more closer to the nucleus? I mean whether it is 2s or 2p. Last class only we have seen na ns, np, ndf, then penetration power was for ns it was more, right? So here I'll say that the electron affinity for this is going to be more, right? So I can say that if penetration power increases, then the electron affinity also increases. Here you have to add to 2s, here you have to add to 2p, right? Remember, I'm just writing it again. Penetration effect or power ns, np, nd and nf. Here n is same. Getting it? For n value same. I hope it is clear to you, right? So if the penetration power increases, then in that case it becomes more easier for that particular species to accept the electron, because 2s is more nearer to nucleus as compared to 2p. So where more nuclear force of attraction can be felt? On 2s as compared to 2p. Yes, hopefully people have written this. Quickly write it. Let me proceed further now. Now next is trends of electron affinity in periodic table. Now when we talk about trends of electron affinity in periodic table, so as such there is very irregular trend, but what I'm going to write down here is it will be better if at all I'm writing here general trend, because this is one such property which is having very irregular trend. Okay, so in a period, if at all we are moving from left to right, so what we are having basically here, left to right, Z effective is going to increase, and because of that what is going to happen is electron affinity is going to increase. In a group, I'm just writing the in general properties here, top to bottom when we talk about. So what is going to happen? Size increases here, and I'll say that the electron affinity is decreasing in general. That's what is the general trend. So here I'll be just talking about few of the trends, okay? Some important trends we'll be talking about, from where you can expect a little bit of the questions, right? Rest much not is asked. Now, few important trends of electron affinity in periodic table. Let us just see one by one. Suppose if at all I am talking about second period, right? In second period, I am having lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine and neon, right? If I talk about its configuration, it will be 2s2, 2p6. Here it is 2s2, 2p3, and here it is 2s2, right? Now the thing is, if at all I want to arrange for the electron affinity, so you would have definitely got the idea that these elements which I am talking about, they are going to have like maximum trouble in accepting the electron because of their stable configuration, right? Now in that also, you are having neon in the end, then the beryllium, and then the boron, then this particular nitrogen, right? Reason being, neon completely filled shell, right? Here it is also like S, this is completely filled subshell. What you are having here is half filled. So that is the reason we have arranged it like this. Then what are the elements left? Lithium, boron. Just now we have seen for lithium, it is like 2s1 you are writing. Here you are writing 2s2, 2p1. According to penetration effect, it will be like more liking for lithium to accept the electron, right? Rest is carbon, oxygen, fluorine. Apply that Z effective. As Z effective increasing, the electron affinity also increases. Okay. Now, let us proceed further, which is for the third period. So you are having sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, and argon. Okay. Now in this case, what I'm going to, I have just, identified those elements from here for whom it was the electron affinity which was negative. For rest of them, it was positive. Now here, negative for magnesium and argon. Now if at all I want to arrange the electron affinity, it will be like argon less, and then it will be magnesium. Now coming to sodium and aluminium, apply the same effect which you have applied for lithium and boron. So in that case, sodium will have higher electron affinity as compared to your aluminium. So I'll be writing aluminium and then sodium, right? Now after that, what is remaining? These are the elements which are remaining. Okay. Now the thing is, here you will be writing this as 3s2, 3p2, and this is 3s2, 3p3. So among these two, basically silicon will show more electron affinity because what it is having, if it accepts one electron, it will have that stable electronic configuration, right? So the thing is, I'll be writing phosphorus has less, and then silicon, and again sulfur and chlorine, it will be based upon the Z effective only, right? So kindly note it down. Yes? Okay. Now let us write down about one more thing. Electron affinity of third period elements, that is greater than the electron affinity of second period elements. Now when I'm talking about this, I'm referring to valid for p block element only, right? So what I've written here is, suppose if I want to write down second period p block element here, second period and third period. So you are having boron, carbon, nitrogen, oxygen, fluorine. Here we are not talking about inert gases. Because every time I am telling you that we are going to compare the negative electron gain enthalpy. Negative electron gain enthalpy means the elements which have positive electron affinity, right? Neon, argon, all those stuff, they do not, all those elements, they do not show any electron affinity. That means they have negative electron affinity. So that's the reason we can even consider that to be zero, right? Now here it is boron, aluminium, carbon, silicon, oxygen, sulfur, fluorine, chlorine, right? Okay. Now what we are saying is, if at all I have to go for electron affinity order, so that is the order. Are you able to see? This arrow is telling the electron affinity order. That means electron affinity of chlorine is greater than fluorine, of sulfur is greater than oxygen, of phosphorus is greater than nitrogen, and of silicon is greater than carbon, and aluminium is greater than boron. That's what we are talking about. Now let us try to understand why, right? Now when it comes to fluorine, suppose, right? Fluorine is 1s2, 2s2, 2p5. When it comes to chlorine, it is 17, which is 1s2, 2s2, 2p6, 3s2, 3p5. Now the thing is, both have a tendency to accept one electron, right? Now you identify in this case, fluorine being small in size, first of all, it shows more electronic repulsion for the incoming electrons. That is the reason its electron affinity decreases. Or else, you could even think like this, 2s and 2p, what is the maximum capacity of the electrons there? 8, right? 6 plus 2, 8, maximum. Na? In 2s, 2 electrons, and 2p, 6 electrons at max, right? Now, here if at all you talk about, so you are having 3s, 3p and vacant 3d, right? So in 3d, you can easily accommodate 10 electrons, and here there are 7 more remaining. So that means there is total 18 electron capacity when it comes to chlorine, because you are having 3s, you are having 3p, you are having 3d, right? So total how many? 2, 6 and 10. 18 electrons could be accommodated here, right? So now you imagine a scenario. Suppose there is a room which is of like 8-member capacity, and the other room is 18-member capacity, right? And in this 8-member capacity, already 7 people are existing and one more is trying to enter, right? So there will be like more repulsion, because one bed or some space is empty, so people will be already comfortable chilling that okay, at least we are having some extra space for us, right? So if one person extra, like one person is about to enter, which is the last member here, so he'll be getting maximum of the backlash here, because the thing is people are going to show more repulsion here. They don't want that person to enter. Okay, now when it comes to 18-member, if you see, already how many members are present there? 7 members, but still there is like place for 11 members more, so there is lots of room, right? So what, lots of space there, I am saying, right? So what will happen is, if at all now one electron wants to enter here, definitely some repulsion could be there, definitely it will be there, because what will happen, already 7 people there become friends, right? Now some newbie is coming, so definitely there will be some kind of friction which will be there, but that's okay, right? But at least not in the case of repulsion which that person will be feeling here, right? So that is the reason we are saying that chlorine will have the higher electron affinity over fluorine. And this is very important, because majority of the time questions could be asked on this fundamental only, right? Make sure you are writing this. Yes, hopefully people have written this. Okay, good. Now next is, there are like few important orders when it comes to only the groups where is little bit where it is regular, because electron affinity, it will be like totally based on the data which is there, because there, I already told you, this is one such property which is having very much too much of irregularity, right? So here, suppose if at all I am talking about group 17, right? In group 17 you are having fluorine, chlorine, bromine and iodine, right? Normally what we should expect, that when we are going down the group, the electron affinity should decrease, which happens, right? But in case of fluorine and chlorine, chlorine is having higher. So if at all I have to write down overall order, so chlorine is greater than fluorine, and then you are having basically bromine and iodine, right? So do remember this, chlorine, fluorine. Okay. Now when it comes to group 16, you are having oxygen, sulfur, selenium and tellurium. So normally what we feel, that basically it is going to be When you go down the group, it decreases, right? But here, oxygen, it is having minimum electron affinity when it comes to in its group, right? So here what I can write is, this will be sulfur, selenium, tellurium and oxygen. That is the overall order, right? This is what is the order. Overall electron affinity order. Okay. Now for group 15 I am writing here. For group 15 you are having nitrogen, phosphorus, arsenic, antimony, and it is seen it is increasing down the group. Increasing in the sense, for this electron affinity is negative and for them electron affinity is positive. Rest for any members I am not writing, and whatever orders I have written, they are purely based upon the values which we have for the electron affinity. Okay. And you might get doubt, ma'am, nitrogen and phosphorus, like they all are coming below nitrogen. When nitrogen doesn't show that electron affinity, right? How come phosphorus, arsenic and antimony? When you look for phosphorus, you are having vacant 3D there, right? So it can accept the electron in that vacant 3D subshell, okay? So please write this, then I'll give you 1 or 2 questions for this. Okay. So I'm going to give you a question. Arrange the following elements. In fact, you can write down one more point here before we go further. Chlorine has highest electron affinity in the periodic table, or else we can say highest negative electron gain enthalpy in the periodic table. Huh? So chlorine is that particular element which is having highest electron affinity in the entire periodic table, or else highest negative electron gain enthalpy. You will see that there is one particular table which is given in your NCERT which you can refer to. There you will see that it is minus 349. So highest amount of energy is liberated when chlorine is accepting 1 electron. Okay, clear about it? Arrange the following elements in decreasing order of their electron affinity. Suppose I am writing carbon, nitrogen, oxygen and fluorine. Second one is, or else let me say, boron, carbon, nitrogen, oxygen. You are having aluminium, silicon, phosphorus and sulfur. Electron affinity order you have to tell. Out of this first one, definitely nitrogen being least. After that, you just apply the Z effective for the rest of the elements, boron, carbon and oxygen. Here, aluminium is a metal here as such. So metal will not show any tendency to accept electron. So aluminium I am keeping at the end. Coming to silicon, I have given you 2s. This is 3s2, 3p2. This was 3s2, 3p3. So basically phosphorus will have lesser than silicon and then sulfur. That should be the order for electron affinity. In fact, here I have written the increasing order, or else you can think of, okay, starting from that, it will be decreasing order. Hopefully it is clear. Then one more question I am giving you. The ionization energy of sodium is 5.1 electron volt. What is the electron gain enthalpy of Na plus? What is the electron gain enthalpy of Na plus? Yes, majority of you have given the question answer for this. You are having this Na plus electron. For this, they have given you ionization energy, which is 5.1 electron volt. Now, are you able to see that here ionization energy is always the energy which you need to give, right? Endothermic process. Can I say here delta H is, in general, delta H is 5.1 electron volt. Hai na? Now, if at all I am writing the electron gain enthalpy, this is what is electron gain enthalpy of Na plus. Yes or no? The reverse of the first reaction. So is it not the reverse of first one, that is reverse of this, which is minus 5.1 electron volt? Getting it? So that's your answer. Okay, one more question I'll give you. Which of the following process is endothermic? First one, second, fourth is all. Endothermic I have asked you here. So in all of them, definitely this is also endothermic, this is ionization energy, this is also endothermic. This is overall, it will be endothermic only, so it has to be all, right? Similarly, they can ask you which of the following processes exothermic, right? Okay, so with this we finish off the electron affinity. Now we'll proceed towards the another property, which is electronegativity. Electronegativity, which in short we'll be writing as En, right? And the symbol for that, actually ideal symbol is chi. We say this as chi. En is our shortcut as such. Now when I talk about electronegativity, let us say I'm having a particular AB. That means AB molecule, you can say. And here I'm having a bond which exists between them, right? In a bond, definitely, you know, it will be 2 electrons, right? If at all the electronegativity of them is like same, so the electron cloud is not going here and there. It is like shared equally between them. That is, there is symmetrical electron cloud which is present between A and B. Now, if at all I'm writing electronegativity of B is greater than A, right? So in that case, what will happen? This electron cloud will be slightly shifted towards B. Are you getting it? So you are going to have like delta plus and delta minus separation here. This delta minus is telling you that this particular electron cloud has slightly moved away from A, but it has not totally entered into its atomic orbital. I'm not writing A plus and B minus. Getting it? I'm just writing delta plus, partial positive charges and partial negative charges, which I'm writing here. Okay. So here I have written electronegativity of B is greater than A, right? So what are you able to see here? Why this delta minus or delta plus has come? Doesn't it feel like that this B which is there, it is pulling the electron density towards itself? From where? Basically from that covalent bond which exists, right? So this tendency only we are naming it as electronegativity, right? So the tendency to attract the shared pair of electrons, when I say shared means it is in a covalent bond only. So the tendency to accept or else attract the shared pair of electrons towards itself from a single covalent bond is known as electronegativity, right? So I'm writing down here the definition for it. The tendency of an element to attract the shared pair of electrons from a single covalent bond from a single covalent bond towards itself is known as electronegativity. Now, before we proceed further, we must know the difference between electron affinity and electron negativity, because just now we have finished electron affinity. Now when we talk about electron affinity and electronegativity, I say that electron affinity, it has absolute value, here has relative value, right? It is defined for bonded state and here it is defined for isolated gaseous atom. Okay. And electron affinity, it has units of energy and it is unitless. Right. So you just try to understand one thing. Electron affinity, what we said, it is basically whatever are the energy changes associated, or is the energy released when an isolated gaseous atom accepts the electron, right? So it is having the units of energy, right? And it is for isolated atom only, right? And it has got absolute value. That means for each and every element, I can say what is the absolute value of it, right? How much is the electron affinity associated? How much is the energy liberated or else accepted by a particular atom? That has absolute value. Now, when I talk about electronegativity is basically, I am saying it's a relative value. Relative value means you will realize soon that on the Pauling scale, basically we'll be taking the reference of like fluorine there, right? So based on that, we are going to, kind of have the values of electronegativity for rest of the elements, right? So relative to a particular element. And relative, it all depends like in which particular, with which particular element, that particular element whose electronegativity I am talking about is attached to or bonded to. So it is a relative value. Now, definitely it is only defined for the bonded state and definitely you are not going to see any unit of it because it is just a tendency. So tendencies don't have any unit. Okay. I hope it is clear. Please make a note of it. Yes, are we done writing? Okay. Let us proceed further for factors affecting electronegativity. First one is Z effective. Again, here also you just see all those factors which were affecting, the tendency to accept the electrons. Similar way here also. Only thing is here, electrons are not getting accepted. They're just getting attracted. That's the difference. Accepting means the electron is totally coming from one atom to another, right? Here, it is only attraction. So, delta plus and delta minus charges will be there. So, if at all Z effective increases, size decreases, and the electronegativity is going to increase. Second one, you are having basically N, that is number of shell. If N increases, what is going to happen? Size is going to increase and accordingly electronegativity is going to decrease. Then you are having basically for stable electronic configuration also you don't have any kind of electronegativity here. And depending upon percentage S character I am writing here. percentage S character. That means, see, when I'm talking about isolated atom, I'm having S, P, D, F. But when I'm talking about bonded state, definitely what you are having is hybridized orbitals here, right? So if at all I'm having SP, SP2, SP3, if at all I have to calculate the percentage S character. So in this, out of two orbitals, I am having one as S. So what is the contribution? 1 by 2, which is 50% here. Here it will be 33 and here it will be 25. Are you getting this? This is 1 by 3 into 100. Or else this will be 1 by 4 into 100. So that's why you are getting 25%, right? Now what we say, that percentage S character or is the electronegativity is directly proportional to percentage S character. That means, why I am saying so, because that S, which S orbital or S subshell which you are talking about, that is more closer to the nucleus. If it is more closer to the nucleus, I'll be able to say that it is going to be getting like more attracted, right? So the electron will be easily able to get attracted if at all percentage S character is more. So make sure you are writing this. There is one more small factor, positive charge on the atom. So electronegativity is going to be higher if at all positive charge on the atom is higher. Suppose if I ask about Pb plus 2 and Pb plus 4, whose electronegativity is going to be more? Which is more positively charged, right? So these are few factors on which your electronegativity is depending. Make sure you are writing this. Okay. Now let us write down about general trend of electronegativity in the periodic table. And when we talk about general trend in a period, when you move from left to right, what happens? Z effective increases, and if that increases, what is going to happen? Electronegativity is going to increase. In a group, top to bottom, size increases in general, and we say that the electronegativity decreases. Like, before we proceed even more further into more trends, I'm just going to write down different scales for determining electronegativity. So basically, as such, you just have to remember the values. You don't have to go for any fancy thing there, right? So what we are having here is Pauling scale, and Pauling scale being the most important here, right? And you just remember that this particular scale, it is based upon bond energy data, okay? So it is based upon bond energy The thing is, the equation, that is not much important. That is the reason I'm not giving. But the order which I'm going to give, you have to remember that. So you're having lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine. Here I'm writing hydrogen, sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, bromine, and iodine. For these elements, you must remember. Okay. What we are doing is, for fluorine, write down 4, then keep on reducing 0.5, 0.5. You'll be having 3.5, 3, 2.5. You'll be having 2 here, 1.5 and 1. Then decrease 0.1 here. So you are going to get 0.9, then add 0.3 here, again 0.3, again 0.3, again 0.3, add 1 time 0.4, which will be 2.5, and this one will be 3. Are you getting it? What I've done is, I have added 0.3 here, 0.3. This also 0.3. This also 0.3. This also 0.3. So you have to add 0.3 4 times, 1 time 0.4, and then 1 time 0.5. Now this is 2.8 and here it is 2.5. You must remember these values, and here you are having 2.1. 2.1. Getting it? You must remember this value. Here what we have done, continuously you are just subtracting 0.5, 0.5 from here. And I told you that it is a relative scale. That means for fluorine they assumed it is 4, and then they have gone for giving for rest of them. So from fluorine you go up to lithium by subtracting 0.5, 0.5 regularly, right? Then from lithium to sodium you subtract 0.1, you will be getting 0.9. Now 4 times you add 0.3. 1 time you add 0.4 and 1 time you add 0.5. Getting it? And it is simple to remember. 3 minus 0.2, you're having this 2.8 and again 0.5. Yes? Hopefully written. Good. Next one is Mulliken scale. So Mulliken scale is basically based upon ionization energy and electron affinity. So what he said, that the electron affinity plus ionization energy upon 2 is basically the electronegativity, right? So it is based upon electron affinity and ionization energy, right? And you must remember that the electronegativity on the Pauling scale is equal to electronegativity on the Mulliken scale upon 2.8. Right? P stands for here Pauling scale and M stands for Mulliken scale. Right? So make sure you are writing this. Yes, are we done writing? Okay. Now, some trends of electronegativity in the periodic table, right? Suppose for the first one, group 1 I am having. So lithium, sodium, potassium, rubidium, cesium. It shows a regular trend. That means when you are coming down the group, size increases and the electronegativity is going to decrease. For group 2, if at all I talk about, similar trend. Beryllium, magnesium, calcium, strontium and barium. Again, electronegativity is decreasing. No problem with this group 1 and group 2. Okay. Then comes the culprit, which is group 13. Right? In group 13, boron, aluminium, gallium, indium and thallium. If at all I look for the electronegativity value, it is 2, 1.5, 1.6, 1.7 and 1.8. So normally it should decrease, but what you are able to see is electronegativity order here: boron, then thallium, then indium, then gallium and then aluminium, right? So basically maximum irregularity is coming here again because of the poor shielding effect of d subshell electrons, here again because of the poor shielding effect of 4f subshell electrons, right? So just in case, then if at all I am talking about group 14, carbon, silicon, germanium, Sn and lead. So down the group it should decrease. Then it is found that it is for them it is same, but Sn and Pb again it is increasing because of the poor shielding effect. So overall order will be carbon. Then basically you are having lead and rest of them silicon, germanium and Sn. For them it is almost same. Then when I am talking about group 15, nitrogen, phosphorus, arsenic, antimony, bismuth. Now in this case, definitely it is decreasing. Here it is almost the same, right? Then group 16, there is no exception here. And group 17, fluorine, chlorine, bromine and iodine. Again, there also there is no exception. So make sure you are writing them. Written. In fact, these orders, it will be useful when you go for learning your block chemistry. So there only the atomic properties we will be learning, no? Now let us go for the application of electronegativity. First application being in case of inorganic nomenclature. In case of inorganic nomenclature, what do we mean? That means always a more electronegative element, from that only we'll be expecting that anion will be formed and its name should be ending with IDE, right? So basically if at all I write down something like NaF, so I'll be writing this as sodium fluoride, right? So what you're able to see, fluorine being more electronegative, right? It will be F minus. More electronegative element name should end with IDE. Suppose if I write K2O, so this is potassium oxide. If at all I write OF2, I'll be calling this as oxygen difluoride, right? Mind it, I won't be calling this as oxide of fluorine. This is wrong because fluorine is the most electronegative element here. Okay. Now, second one, in case of oxidation state. So definitely for determining the oxidation state, we need the help of electronegativity. The one which is more electronegative, that element will have negative oxidation state, and the one which is less electronegative will have positive oxidation state. So I'm saying that more electronegative atom, negative oxidation number. Less electronegative atom, we are going to have positive oxidation number. For example, when it comes to NaCl, right, we are writing this as Na plus and Cl minus. Able to see that? If at all I have to calculate the oxidation state of H2, like sulfur here, so I'll be writing 2 plus X equal to 0, X equal to minus 2. Do we know that here sulfur is more electronegative? Getting it? Similarly, if at all I am writing something like H2O, I know it is minus 2, here it is plus 1. I know that the electronegativity of oxygen is more as compared to hydrogen, right? Now next application is percentage ionic character. Now when it comes to percentage ionic character, basically what I'm saying is, suppose if at all I write something like NaCl, I'm writing HCl and I'm writing ClCl, right? So are you able to see here, I'm saying this is ionic compound, right? Because I'll be able to write here Na plus and Cl minus. Here I'll be able to write delta plus and delta minus only. I won't be able to write H and Cl, H plus and Cl minus. Now the thing is, don't think here, ma'am, here it is like HCl, we know it is a strong acid, but everything in water. I'm talking about HCl gaseous. Here it is 0, 0 you are writing, okay? Now the thing is, here what you're able to see, as delta En increases, what is happening to the percentage ionic character? Percentage ionic character increases. This is ionic compound, this is like polar covalent compound, and this is like non-polar. Are you able to see this? This is polar covalent compound and this is non-polar. This one is ionic compound. So here in fact I should have written like here ionic, this one is, if this decreases because the arrow is going in some other direction, I should, if at all I put this arrow like this, then it is fine. Otherwise, as the electronegativity differences goes on decreasing, what is happening? Ionic character also goes on decreasing, no? Getting it? Or else, if at all I would have put this arrow like this, starting from Cl, Cl to NaCl. So at that time, I would say that the electronegativity difference between Na and Cl, it is more, so it is more ionic, right? Now for determining that percentage ionic character, there was one scientist, Hanny-Smith. So they have given the equation, Hanny-Smith equation. So percentage ionic character is equal to 16 mod of delta En plus 3.5 mod of delta En square. Right? So basically this is the equation and you just have to, kind of, okay, you must visit this equation. That's the only purpose of it. Okay. So from here, what was the conclusion? If delta En is equal to 2.1, then it tells you it is 50% ionic and 50% covalent nature. Right? And if delta En is less than 2.1, in that case, it will be like predominantly covalent, or else you can say that the covalent character is more here. Covalent nature greater than ionic nature. If at all this delta En over here is greater than 2.1, I'll say that the ionic nature is greater than the covalent nature. That's what is the conclusion from here. So make sure you are writing them down. Yes, done. Now fourth application, to determine the behavior of compounds containing OH bond in water. That means suppose if at all I am writing MOH, NOH, right? In water if at all I go for, in water. And I am saying this act as Arrhenius base. And here this act as Arrhenius acid. Right? Now N represents non-metal. This represents a metal. Now what I'm saying here is this bond is breaking. Here this bond is breaking. That means why a particular bond will break, it will depend upon the electronegativity difference. So can I say here the electronegativity between oxygen and M and the electronegativity between O and H, which is more? Definitely this more. Whichever is more polar bond, it will be attacked by this polar molecule, right? That will be breaking down. That's why OH minus will be separated out. Here basically it will break down as NO minus plus H plus. Because here the electronegativity difference for OH bond is greater than the electronegativity for the ON, right? And here this will be breaking down as M plus and OH minus. That's what you see in your day-to-day life. NaOH, if at all it is written, you will be writing this as Na plus and OH minus. Because the electronegativity difference between this Na and O is more. This is basically the ionic bond which exists. Now when it comes to suppose HOCl, we will be writing like this. This will be H plus and OCl minus. Right? Yes, so we are done with the kind of, application of this electronegativity. There is one more which I would like to write down to determine polarity of bond. That means if delta En is 0, then you are having non-polar bond, and if at all delta En is not equal to 0, you are having polar bond. For example, if at all I write suppose H2, so delta En is what? 0 here, so it is non-polar. If at all I write something like suppose HCl, delta En is not 0 here, so you're able to see this is polar bond, delta minus, delta plus. Clear about this? So that's all for today's session, okay? And we'll continue from here in the next lecture. I think in the next lecture, probably we should be able to finish off this entire chapter, okay? So till that time, just revise the concepts which I've given to you, okay? And enjoy your day and definitely study nicely, okay? Thank you and have a nice day.